Alright, first video, and here we go. All nodes distance k in binary tree. Given the root of a binary tree, the values of target node and integer k, return an array of the values of all nodes that have a distance k from the target node. You can return the answer in any order. You have some nodes, a tree, you have a target node, and this k. You need to find all the nodes that are at distance k from the particular node. We have 5 and we can go. We are finding 1, we are finding 2, we are finding 7, we are finding 4 in this distance. So we have 3, 2, 7, 4 and plus 1. Just need to find the distance between all the nodes. How can we? Okay. Now this is a 5, this is 1, this is a 3, we can't move up and down. No, we can move down, but can only move down, we can't move up. There's no relationship between this 5 and 3 apart from parent child relationship. So moving from 5 to 3 is not possible in this structure, and I need to reach this one. If I go for LCA, lowest common ancestor, of this particular node, that is 5 and this is 1, and then I find the LCA, and if but that will not make sure that the distance is k, so that would be a wrong approach. So I'm standing at 5 and need to reach 7 and 4. I can reach left and right and count the number of nodes. That's pretty easy. But the particular fact is that I need to reach these nodes that are not particularly the child of this node. And if they are not the child of the node, then there should be a relationship that needs to be established between them. Let's try to draw the structure here. We have a node, kind of it looks like. Just hold it here. Yeah. 3, 5, 1, 5, 1, and there's this node and this node, and then I guess there was this, and there was something like this. Now I'm standing at 5 somewhere here. I can reach here, here easily just by moving left and right. That would be pretty easy. But the issue part is going here and then here. This can be done. This is just going from root node to the right node. That's easy. So this particular traversal is not an issue. This is not an issue. This is not an issue. The issue is going from here to here. If I just convert it into a graph, so there is a edge between here and here. So I just make it a kind of a undirected edge, or a yes, two direction edge or undirected edge. So if I just undirected edge from 5 to, now I can go to 5 to its parent. So that would be pretty great, right? So I go from 5 to my parent. So what kind of relationship I would need? I would just create adjacency matrix like a graph. So for adjacency matrix, if I create a graph where I have this node and what is parent, or you can just make a parent child kind of relationship. Now we just need parent. Every node will find its parent. So what kind of that would look like a recursion, something like this. I have this node, and all these child nodes. I will start from the top. There will be -1 for the root, and then I go here. I will ask who the hell is your daddy, and then it will be like uh, that this node is my father or daddy, something like that, and then this, and then this, and it will just a simple recursion, right? Simple recursion that will start somewhat -1 because it's a root node, so we need -1 to start here. You can start from left and right also. but there will be two recursions. To avoid that, I think -1 is the best approach that I can think of right now. So if I just take -1 here, put my nodes here, and just have a recursion something like, okay, let's say if I, okay, where's the text? Something like void. I have the node, I ask the parent, and then just I keep solving like something like this. Okay, this is the step. If I go there and just, if not node, what will be happening? Why worry about not? What we will deal with later. Particular fact that we need to worry about is particular node. We'll just check parent not equal to -1, and we can work further. We can just make our matrix. Yes, we can have a matrix adjacency node is equal to parent. It will hold its parent. So, and then what we can do is just call this. What am I going to call this particular thing? I was going to call it solve. Solve will be called for left, and similarly solve will be called for right with their parent. Or we can figure out some other way. So let's try to code this. Now this one is a different problem. We'll solve it later, not right now. Okay, so there's something like this. We need a parent-child relationship in our node, and we need to make sure that we have something to work on. Okay, so as I thought, I will create void type function. Let's name it as solve. First time for more is hitting hard. Let's just pass free node star root. What about the parent? Let's deal it with later. Let's first create a graph, and it will hold a tree node, and then it will also hold a tree node for this also. What we name it? Let's name it parent. Now what we need to do is solve this particular fact. We have a node, tree node, and I'm not passing a parent. If I'm not pass the parent, then what should be the code? Every tree node will have a root left or root right. So if root left, then parent of root left would be root itself, right? And if root right exists, then parent of root right would be equal to root. Now I need to call the recursion here. Just call it right down here. You can call it right down here. I can call it even outside. So we just need to call it solve, and we'll pass root left, and I will also pass solve root right. Now it is not necessary that I'm passing it then the root like this. So if not root, so just return the code. There's nothing that you can do. I guess that would be pretty satisfactory for this particular thing. Now what I need to do is the traversal part. I can write a simple BFS or DFS. Okay, so void solve 2. I am the parent. I just need node start target here and key. Sometimes this small key, large key makes quite confusing. And then for holding the result, I will use this array vector int at the rate result int at the rate and void solve tree node target result. What will be the result be holding? Say result will be holding result will be holding the nodes that are at distance k. Okay, so now if this is a node and this is a k and this is a result, I can write a sweet DFS for this, but let's go with BFS. So for going with BFS, I need a Q. Q U E U E. Why it's so long? Free node star. Okay, free node star. Let's name it Q. The most organic and genuine name that I can currently think of. Tree node Q. And in Q push my target. That's the first node that I need to push. Now what I need to do is move in this queue and just walk around with this queue. So what I need to move in the queue, right? Not queue dot empty. Just a generic BFS will do the job. I minus minus. I pick the, the front of the queue called node is equal to queue dot front. Okay, now this node is my queue dot front. I don't need to do anything special about this. Do I need to push it in the my result vector right now? I don't think so. I need to push it my result vector. Need to pop this out of the queue. Now what I need is to do something. Okay, so I'm not pushing in my result right now. So when shall I push in my result? Why should I push in my result? I will push in my result when I reach k distance nodes. Okay, so I will push only when I am at k distance nodes from this particular node. So you would pop it, and I just need to now check the particular thing that if node left exists and and k. No, I've checked k. What if I've already visited this node? So to avoid this, let's make a set here. What's the type of set that we should be pushing tree node or the value of the node? We should be pushing tree node. No, we should push the value. State. If this is the thing, then visit it dot insert target dash val. Also visited and not visited. Visited. So it's a set is a count, not a map. So not visited node left val. That's right. I have not visited this particular node. Just need to do this. Q. Why the hell I'm typing? Push. Cur- No, it's not current. Let's just say it's node. Q dot push node left inside the queue. Now I need to do the same for the right side. Node right and not visited account node left dash well. I need to cool it. Cool it second node right. Just now if parent dot count of node exists and not visited count parent node val. If the current node's parent has also not been visited, then just push it in the queue. That would be parent that node. Now, queue the push parent of the node. This is queue. What I need to do next is not decrease the key. So if I had k, so every time I do this, I should be decreasing my k. So these are the nodes that I have visited so far, and if every level is successfully visited, I will decrease the k. Now every time the code restarts, I just need to check if k is equal to 0, then just break out of this. Okay, now I break out of this. Now I have a queue filled with the nodes that are at distance k from my current node, target node. I just need to push them in my result. So why not q dot empty? I will go. I will take a tree node star called temp. That would be q dot front and this q dot pop, and then I just need to push it in my result. Push back temp hash well. Okay, so now push all the nodes at distance k from target in the queue. Okay, so this is the queue. This is the particular part. We have solve one, and I think I have named them both solve. Let's name this solve one. This is solve. So I need a vector that would be result, and then I will call solve and pass my root node in that, and then I will call solve one. That would be my target node. Then what I'm passing there is the key, and then it's the result array, and then I just want to return the result. Okay, so now if I don't get a compilation error, some sort of if k is equal to 0, okay, it's not JavaScript, it's C++. Okay, okay, what we getting? Wrong answer here. I'm pushing an extra node, in which case it's just saying that I have two nodes. I'm pushing a one extra, right? I'm pushing this node is late 5741 and this is 741. Okay, output should be expected. Oh, I'm missing a node in this particular case, so one should be going there. I pushed the parent node there. Why not n minus minus? What's the issue with the code? Parent node. There's some sort of issue with the parent. If parent not working well, if not root, then I would return. If root left exists, then I call. I just try to play this calm. Root left. We put the root. Then I call the sort function again for root left. Then if there's a right, I'm getting root. Right is equal to root, and then solve this. Not root, then I'm returning it. Ordered map tree node. Okay, this is kind of annoying. Why is it not just try to just see why it's not working? Ordered map tree node parent. Okay, put it there back. What kind of issue I'm facing? I'm not able to visit. Why then? Minus minus take the Q front out. Parent count node. Parent is in the node. I'm not visited count parent node val. Then I just okay. I think this some sort of issue. First thing first, I have not marked any of this node visited. So visited dot insert. That would be parent node dash val. Then again visited dot insert. Okay, what would be inserting? That is node. What is right? Okay, there are quite a lot of issues, I guess. Right val because it should be right, not left. And then again, I would be visiting visited dot insert same visited, right? And sometimes I think there should be auto suggest for this spelling part. This no, this oh no. When the spelling will get wrong and that's okay. So I was missing this particular part in my code. That's the first thing that I was missing. Mm, I take a note. Node is equal to q dot front. I pop it out with node left axis parent count. It's my parent function working well. Let's retry this. How do I get the same error? I guess I will get the same error. No, I did not get the same error. So compilation error here. Uh, is it here? Why such a hurry? Okay, it's worked. So it works, I guess. Just let's comment something. Building parent child relationship, finding keynotes at finding notes at distance key using BFS. Now let's try to submit this. Okay, let's go with this. Submitting. Oh, good. Okay, pretty good. We are done with this one. Binary tree cameras, amount of time from binary tree to be infected. Let's go with this one, or let's go with this one. Don't know what the next problem that count all possible routes. It's a hard one right now. I'm not in the mood to solve hard problems. Binary tree maximum pass sum. Binary tree cameras. All of these are hard. This is a medium one, but if you look closely, it's a medium one. It's a hard one. It's a medium one, which we would do. Let's go with this one. Binary tree maximum pass sum. So let's separate the problem. A path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum of this is the sum of the nodes value in the path given the root of a binary tree. Return the maximum path sum of any non-empty path. Okay. Okay, so let's solve this problem. We have root 1, 2, 3, and the optimal path is 2, 1, 3. Okay, 2, 1, 3. So we can make a relationship like this 2, 1, 3. Okay, if it goes like this, then we can create a map and then just go around and just call this as sum. Go from any node and find the maximum path sum that we can reach. Let's see the other case. We have minus 10, we have 9, we have 20, we have 15, we have 7. It's pretty visible that this would be the sum of the tree. We have 15, 27. Kind of R kind of thing. Okay, so here's the path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting to them in the sequence. A node can only appear in the sequence at most once. So if a number can appear only at most one in this particular tree, then I can go like this is a path, but if I go, I can't go with this 9 because it's minus 10 is here. But if I decide to go from 15, 20, I can go this path. I can go this path. Okay, I can go many paths, right? Okay, let's take an example. Control A backspace. Okay, now I have this tree node. I have, let's say, many childs. Uh, like this, I have this, and then I go this, and then this, and there's this node also. Let's go kaboom here. Kind of like this, right? I have this node and this node also. And I need what to do is to find the pass sum in this tree, and that needs to be maximum. Okay, so I need to find the maximum path of the sum in this particular tree. I don't know where the path sum will lie. That's a particular issue because in this whole tree, this sum can be lying anywhere, right? In this particular tree, this sum can be lying anywhere in the tree, right? So the most simple case that is given to us is kind of this A kind of shape that is formed, but we can go here and here, and then here. This can be a max pass sum, or I think we can even go here, here, and then this here. This can be a maximum pass sum, right? Let's try to draw it a little bit of code. We have a tree node, another tree node here, tree node here, and if this tree node has a very high infinity value, then we don't want this. We want to go here, 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 here. Now if I convert this tree into a graph like my last question, it's not optimal to convert every tree into a graph. That problem I think was only solvable by using that particular thing, or was the only approach that I could think at that particular moment. But if I convert this particular tree into a graph, then there would be an edge between every node, and then I will start a traversal, and from every node I will go and find the maximum sum that can be reached from that particular node. So if I start from here with a sum, something like this, if this is a sum, then I go here and find the sum. That would be something like this. Okay, that would be this one way of sum. But if I'm at this node, I will go sum here. Okay, this is a path that could be taken. What about this path? I mean to say that with two different DFS that would be going from this particular node. I mean to say this is a node and there is a large path that goes somewhere here, and this is a node, this is a large path goes this. If I go and do DFS over here and then do DFS over here and then just add this particular part, so it would be just left and right sum of this particular node, right? We are just finding the left side sum and the right side sum of this particular root node, right? We are trying to find the left sum and the right sum that I can achieve from this particular node and this particular node call forward. And in that particular sum path, I will add this root and then this. Or should I just go till the DFS and return 0 and then go here and pick the sum here and return by adding this sum to the previous node. Now, if I go with this approach, there's a node that is here. It has two DFS call here, just like this node. It make a call here. Here it returns 0. Here this call also returns 0. Now these two node val will return itself to him, and it will add those values to itself and pass those values to the previous node. And then in the same way I will reach this node. But this is a kind of greedy approach because there can be a large infinity number sitting here, like something like minus infinity exists here. Just for a hypothetical situation, there's a minus infinity sitting here at this particular position. So it will just cancel out all this particular sum that was formed here. And it could be a case that there was a sum that was less than minus infinity. There was this sum that was less than minus infinity but was close to infinity, somewhat close to infinity. So it was a maximum sum that could have been found in this tree. All these sums are not, but this sum was close to infinity. It didn't reach the infinity. This was minus infinity, so it will cancel this particular sum, but it was the maximum sum of the whole tree. Now the fact is, now this is the particular thing that I need to work on is if this is a node and here sits my minus infinity and here is the node that is not my minus infinity, and these are the two nodes that are less than minus infinity. These two nodes are less than minus infinity, but combine these two nodes, they are quite a large sum. Okay, so that's particular thing. This path and this path. There are the cases where this is a solution. In the example, both cases are this kind of a kind of scenario. But what if there's a thing like there's a minus 2 here? Okay, this is a node, it is infinity, this is minus 2, this is, and these are two also infinity, and this is also infinity, and then this is just a zero, plain zero. There's nothing, or this does not exist there. So if I just make a call here, it will return infinity, and if it will return infinity, it would be negative. And then I pass this sum, and this is a particular sum. So this particular whole part is a sum, right? This would be a sum. So I need to make a call here. I'm finding the node here like this. It's my node, and then this is my node, and so what I'm calling is just a left call, and then it would left call for this particular node, and then I make a left call here, I make a left call here, right call here, and when the node does not exist, I just return zero to their to them, and these two nodes will return their value to its parent, and then we will sum those two particular values and return it to the particular parent. But in that scenario, there's an issue that I will miss this particular node. I need to store this value somewhere, so I can just store a result kind of thing. Just in that result, I will store this particular two value or the sum that I formed here. So that can be found in a particular second. But then I need to return the value. Now let's see what we can do for this particular question. Need to find the sum, right? We can just make it kind of a function. Let's name it int solve kind of thing. Int solve, and what I have is a tree node initially standing at the root, and then I will make the call. Now if not root, then what? Then return 0. Why? Because if there is no root, then we're with nothing to do, and I will just call left. That would be solve root left int, or that would be solve root right. Okay, int a shape. It's kind of a shape, right? So this a shape is equal to L plus R plus root val. I got the shape left node, right node, and the root node form the answer. Okay, so left node, right node, and the root node form the answer. This is a case. Okay, but there can be just, let's say, if we have a node like this, we have node. Okay, again we have something like this. This is now this time equal to minus infinity. This is somewhat 9 to power 9, something like that, but it's not minus infinity, so it's not that big of a value as compared. So now this time, and this is 0. If I take this sum, this will be stored in temp sum, that or that a val sum that I have created. And if I go and ask the sum, this particular would be not the rate of answer if I just return this particular path. it would be the best answer. So there can be a case where I need to just return this particular path or this particular path instead of this. That would be pretty easy. That is just uh, one direction is equal to, we'll take the max of left comma right and then add the root value to it. Now that's good. Now I have one direction, I have a shape, and what is the maximum? Just pass it, just pass it here, just pass it. Maximum is passed. Now what I need to do is maximum, it be max of a shape. Okay, max of a shape and one direction, because that's what we are doing. Now I would return max of a shape, because I need to return an answer to my parent, and that answer could be this particular way or this particular way of doing things. Let's change the color for a second. There could be one answer that is going this way, and there could be one answer that is going this way, right? So if I go this way and a shape, the other is one direction. Okay, I've returned max of a shape and one direction, and we are already storing the maximum. Now maximum should be something that is int min, that is the value. Then call the solve function for the root and return the maximum. Let's see. Okay, what happens? What happens? Okay, what's the issue? Return 0. Why is this particular? Let's write it properly. Okay, return 0. Yes. Okay, one more miss same column. Day. Okay, this 41 and this 42 should be 42, and my output is 41. Why? Because 15, 20, 10, 7, right? I should be getting 15, 20, and 7, and I'm not getting 15, 27. I'm just getting one value less, that is 41. Is the error in this case. Let's just take a dry run of this and see what we have. Minus 10, 9, 20, 15, 7. Okay, we have a node. Yes, let me change the color of this pencil. I have a node that is minus 10, and there's this node, and then there's this node. And how many nodes are there? Okay, not this particular question. 15 and 7, there are two more nodes. Okay, this is 9, this is 20, this is 15, and this is 7. Right. I start from 10. Okay, I have 10. I have 10 in my answer. I have 10 because I push my 10 in my call stack. Nothing happens. I push my 9 in my call stacks. Nothing happens. Now there's a null. It would return 0. Now current max sum that we taken it be max sum would be 9, and this particular node will return 9 to its parent. Now 10 has one value, that is 9. Okay, We don't stop here, we make a call to the right, and this particular value has been popped out also. Then I go 20. 20 will then again call 15, and then I 15. Now when I have 15, I again go get 0 here. 0, I go 0. If this is particularly 15 at this particular node, it will return 15. My max sum would be again updated because 15 is larger than 15 is larger. Okay, what's the issue? 15 is larger than the current sum, so it would be becoming 15. Max sum has become 15. 15 has to be returned to its parent node and we need to return 15. Now 15 has been popped out. 7 is pushed. 7 is pushed. It also gets a 0. Then again, 7 is a 0. Then I add 7. Maximum is not updated. Now what I have at 20 is root value is 20. Left sum is 15. And my right sum is 7. Now I have a value that would be 42. That should be my answer. It is stored in the max sum, right? If I am going right, then the a shape value should be stored in the max sum. Now the max sum is holding 42. That's the issue. Max sum is now holding 42 as the answer because at this particular node I have left plus r plus root val. Let's return the value. This is 42. I'm getting it. Now what I need to do is one direction. Then one direction sum is 15 plus 20 and 7. It's obvious that 35 would be returned. Okay, now this is issue. We have 42, 1, and we have second choice, one direction answer. To go with one direction, it would be 35. Right. So I will put with 42. Return my 42 my parent node, and it is 42 here, and it is 9 here plus minus 10, that is negative minus 10 42. It is here 9 42. So 9, it would be minus 1 plus 42, that is 41. So it becomes 41, right? So it is returning the root. Okay, so what's the issue? A shape or one direction, right? But max sum is holding a shape plus one direction. Now it's one direction. Maximum would be coming from this side. That would be 42 plus 10. That is that is that is 42 plus minus 10. That is 32, right? I have 32 and 41. But my max sum should not be updated by this particular thing. Okay, so max sum will be holding the final value. That's the issue. So max sum should be holding somewhat again a max of max have max sum comma, yeah, max of max sum, and this is a shape, this is a bracket. Okay, the bracket is no longer, just a second, this compilation error, I knew that would be happening. Max of max sum. Okay, this issue, this is max of this Okay, now let's see what happens. Okay, it's working, I guess. Now, if I go well with this, okay, so it has failed. Where did it fail? This 2 comma minus 1 comma minus 2, the answer should be 2, but my answer is 1. Okay, 2 comma minus 1 comma minus 2. Okay, what kind of rate looks like 2 comma minus 1 comma minus 2? I have a node. I have 2 minus 1, then I have minus 2 here, right? So if I go with the previous case, there's this one answer, this, and there's this answer, and there's this answer. Now that will be 0, it will be 1, that is 1, and the other would be 2 to 4. 2 plus 2 is 4, and this is, no, it's negative, so 2 2 becomes 0, and then it's minus 1, so then the other choice is 1. So with A case, the answer would be minus 1, and if we go with one direction, the answer coming best is 1. But according to them, the answer is 2. So 2 is a root node, so we can just return a single node also. So that was the case that we were missing. So we can return a single node also, and single node also we can return. So we'll be holding this root val. So I think I need to add a temporary comparison. That would be much better to do. And temp would be max of single node comma max of a shape comma one direction, right now just need to make it temp. Let's see if it works or not. Compilation error, can go. Okay, this time what's the error we are getting? 55 as the output, it should be 48. Output 55, expected 48. This time we are making it bigger, right? Okay, let's copy it. Okay, so this is a kind of tree. This time we are having 5 comma 8 comma 4 comma 1 13 4 11 2 7 2. Okay, it's a bit free. What's the issue? How come the sum is coming 55 when it should be coming 48? We have a node. If this tree is going to be big, okay, just copy this image some way. Just copy this image in some way. If you can just allow me to copy, just need to copy this particular tree. Okay, let's draw it. We have a node 5. Okay, we will just make the tree and then we will type the text. 5 4 11 7 2 is, okay, there's just one left node, and then we have two more nodes here, and yeah, okay, good. And then there's 8 13 4. Okay, and this and this goes here. It's 4 and 8. Okay, so this particular node is 4, this particular node is 8, this particular node is 11, 13, 4. Okay, right? We have 11, we got 13, and we got 4. What again 4? No, there are 2, 4. We have 7, 2, and 1. Okay, then there's 7 here, 2 here, and 1 here. Okay, I hope it's visible, somewhat visible. Let me just zoom in. Okay, that looks something more better. We can just increase the text size. Okay, so now this is particularly the case that we are going to do. Again, we make the call. We have here, we have 7, 11, 2. This whole particular is a positive sum. This would be whole added. Will be summed up here. Will go to its parent. This value will be also added to the maximum, and this would be also added to the maximum. Now there's not a single negative value in this whole tree. So it's pretty clear that we will be just absolutely adding all the values to this particular tree, and then the complete tree is my solution. So it's 55. The answer is the complete tree. Now the particular 48 part. Why 48? Why 48? Why 48? I mean to say, what kind of sum? There's a difference of total 7. 48 and 55, there's a total difference of 7 in the sum. Okay, so there's a total difference of 7. Is this node not being the part, but it would be the part of 7? It is 7. Process our maximum value. So we take the maximum sum here, we find the maximum sum. That would be maximum here, and this would be then definitely added to this particular part. Okay, let's see what's the issue. Okay, they should give the explanation. What is this used for? I don't know. Okay, this is okay. There's no visualization for this particular thing, and I don't know what's happening in this particular case. Okay, from where this particular 7 is coming. A path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that path does not need to pass through the root. Okay, the path sum of the path is the path of the sum of the nodes values in the path. Given the root of a binary tree, return the maximum path sum of an empty path. Okay, so I have this particular path, and then this path, this would be going right. This is going right. Is there any other way of summing this particular nodes and doing this? I don't think so. There's any particular way of summing these nodes. I guess 55 should be the solution here. Why 55 is not the solution here in this particular case? Let's see why. Say I have 11, I have 7, I have 2 as a sum, and then to this particular a sum I have all these values. And why this particular solution is not working? This particular solution is not working. Why? If this is a path and this, okay, so if I go this path, it should be visited only once. I go this, then this, then this. I'm wasting twice. If I am wasting it in a Y shape, then it would be this, and this. If I start here, I go back here. Why did we wasting 11 twice in this particular way? I'm not counting 11 twice, but in a way I'm wasting 11 twice because this is one way and then this way. So it's not this. This is a path and this is not a path. This Y is not a path. I think there's a error in this particular thing. We can't consider this Y as a path. Which is why this particular A would be a option for our sum, but we can't consider this particular case as a path because when I consider this case as a path, I'm saying okay. I start my traversal here. I come here. Okay, good. I go here back. Good. I go here. Good. I consider this particular path good. Now I'm this. And now this is not a path. I'm not going on a single path. I'm making a Y zigzag. It is becoming a kind of a graph net tree. So if I don't need to consider this path as my solution, I don't need to say A as my solution. So if I don't need to consider A in my solution, then maximum would be definitely this, but A would not be here. Okay, one direction, single node. Let's try this. Okay, now let's see what happens. Okay, took some time, but it was a good problem. It was worth the time. Okay, let's write some comments for future. Uh, taking only the root node of the tree. Okay, taking only single node can be a maximum. um, okay, so it can be a maximum. No, I've made a mistake. It should be in this line. Okay, now this particular taking the best of the left or the right. Okay, good. In temp max single node max shape one direction. Okay, choosing the best answer out of all the answers that we have seen so far. We can combine this particular solution. We will for path only consider the case where there is one best node or one way best path. So it's kind of thing that this particular tree, if there's this node, then this node, and then this node, then this node, then this node, and this node, we can have still a like if I want a, it could be like this a. This is one way of having a. Then again, if I want a, it could be of shape like this, and then it might go here, and then it sums over here, and then again just for explanation purpose, our a that might go here, and here, and here, and here. But I don't have the luxury to choose a path like this because this is not a path, it's a Y shape something, so that would not work. That worked. This problem being done. Let's move. The problem is binary tree cameras. Just do it for this particular thing now. Yeah, okay, let's do it. Amount of time for binary tree to be infected, and this is binary tree camera. This one problem that we will solve or count all possible routes. I'm in the mood to solve tree, not these kind of problems. So let's see. Let's go into the topic. Search question. Okay, database, pandas, javascript, stress. Trees, stack, binary trees, or binary trees. 177 problems. 1402 saved. God damn it. Okay, what we have? We have lot of problem. Unique binary search trees, binary tree in order traversal, validate binary seed, recover binary search tree, same tree, symmetric tree, binary tree level order traversal, construct binary tree from pre-order and in-order traversal. Constructing a binary tree from pre-order and in-order traversal, that could be a good question. It will clear many concepts when it comes to foundation. We can solve it. Shall we try it? It's a medium problem. Shall we try it or shall we not try it? It's a question that we need to ask ourselves. That do we need to solve this problem? Binary tree level order travels a true convert sorted array to binary search tree. That's a easy problem. Convert sorted list into balanced binary tree. Minimum depth of binary tree. Let's do this. Pre-order. Oh, no, it's what kind of I open post order. No, I was going to solve pre-order. Let's try this. We have two particular thing, that is a pre-order array. First read the question. Given two integers array pre-order in an order, where pre-order is the pre-order traversal of a binary tree and in order is the in-order traversal of the same tree, construct and return the binary tree. Okay, I have a pre-order array. Okay, one array is named is okay, y sometimes. So y. We have pre-order. Okay, and then we have in order. Now we have pre-order, we have in order. Pre-order is an array. Don't click this, just pick this. We have in order. Now what we have is this 3 9 20 15 7. In what my array? In pre-order 3 9 20 15 7. Okay, so I have 3 comma 9 comma 20 comma 15 and then 7. Quite a space left. Not a issue. No, we can't copy it because the order is different. In the in order we have 9 13 15 27. 9 3 15 27. Okay, we have 9. Okay, okay, just let me. We have 9, then we have 3. We have 9, we have 3, then 15, then 20, then 7. Then 15, then 20, and then 7, right? Okay, this is a 15, this is a 20, this is a 7. We have pre-order, we have in order, and then we want to do is just sum these. No, we don't need to sum these, we need to find the tree from these particulars. Now if you know the pre-order, then this would be the root node, because in the pre-order we go start from the, so 3 would be my root node. That's the thing. I can easily find my root node from the pre-order thing. Now, if you know that in an order, it's a what is a binary tree, binary search tree, or something like that. Construct a binary tree. Okay, on the binary in an order traversal, there's this property that the root nodes, left nodes are present to its left side, and right nodes are present to its right side. That's the thing. So this is a particular 3, and this is 9, this is 15, this is 27. So these are all the right nodes, and this is the left node. That's the thing. Now this is my 3. That is something that I got from my traversal from the pre-order that I know that it would be. Now I need to construct its left. That would be having 9. Okay, that's a thing, and then we have 1527 from here. Yeah, 15, we got 20, and then we got 7 here. Now 1527, this is 9. We can call a recursive function called solve to build this, and pre-order index would be, this would be I something, I index. And then I need to find the root. So to find the root, I will start a traversal in order and find the value in an order, the root. When I get the root value, I know this division will be left side, this division would be right side. So I can divide my array and call a function for this particular thing again. Because this is my left, this is my right. I know this would be building my left and this will be building my right. But the particular fact comes is now how I will find the root of this particular side. If I increase the index here, I come to 9. Okay, that's the thing. I come to 9. In my pre-order traversal, this is my 9. So this is my root. Okay, so in pre-order we go from root to left, and then we just keep moving the similar way, then left, and this kind of thing. Then go right. In an order we have this thing. We go initially into the deepest left and then push that value and then kind of thing. So if this is 3, this is 9, and I need to do is pick this particular part. So I will increase the index and I pick this 9. I find this is a particular node of this 9. Okay, good. Build this as a node. Okay, good thing. Then what? I can't go any further. Can't go any further. Okay, so I will stop this particular thing because there's no return 0 kind of thing. So to stop this particular case from running further from recursion, it could be a void type, but I need to return a tree node, so I don't want it to be a void type. But even if it's a void type, there should be a case where it should return, right? There should be something where it would stop. Okay, so how would I stop? How I will know that this, because if I increase this, it will move 20, and this 20 would be nowhere to be found in this particular site. Yes, this particular 20 would be nowhere to be found in this site. So if this particular 20 is not found in this particular array, I will return back, right? But since I've already returned 20 back here, and if I pass by kind of, if I pass 20 here, I will just stop the case because it's passing I plus 1 to this and I plus 1 to this. In that case scenario, what the issue will be happening is that it will not find the 9 in this particular array, and that case will be just stopped here. So there will be no tree built from this, and then there will be no tree built from this. That's the issue. Okay, just let me erase all this particular clutter to make it more clear. Right. So I can't just stop this particular solution here or here by not finding the value. There should be some kind of pointer kind of thing that tells me when to stop. Initially I have this as 0, this is n minus 1, right? Now I can consider this as start, this is as end, because it's kind of your searching kind of thing. And if my search space kind of gets exhausted in those kind of states, and the kind of binary search quotient, and we have this start becomes greater than end, then it becomes false because search space is exhausted. And in this case the same thing would be happening, because in this particular 9, as soon as I find this 9 and solve this particular node, then the start and end would reach the same node and the search space would be exhausted. Since the search space is exhausted in this case, we would return. Okay, so that's the thing. We have a start and end. We have to make a start and end, and that will point out that my search space for this has been exhausted, and my search space for this has also exhausted. We can just make it this way. So let's try to code this and work it through that. Okay, so I will make a tree node solve function. I have the vector that is my pre-order. Okay, just let me copy paste it. Okay, pre-order in order. Okay, int index, that is something that I have in left and right. Okay, good. Now if my left, my right, if my left becomes greater than right, then I have exhausted my search space. In that case, I want to return a null, because this is a tree that I'm returning, so it will just return a null. That suits it well best. Now, what with the root? It would be the index. So I can get the root valid be, what would be pre-order index. Okay, good. Now I've done this. I have increased the index plus plus. I think I should pass by reference. Okay, then index plus plus. Now what I need to do is find the range for int I is equal to 0 dot I is equal to 0. Oh, I should start from my left. I is less than or equal to my right. Then I will increase it. And if in order I is equal to root val, then break it, because we have found the index for the particular point, like this in the case I would say. Okay, just a second. Okay, this is a 3. I found this index. Now I will break it. So I break it. Once I break out of the loop, I've already increased my index plus plus. You already increased your index plus plus. Yes, and then what I need to do is pick out the tree node stuff root. Should be a new tree node, and it will take root val as a value, and root left. Similar way, solve function will be called again. It becomes easy now because we have reorder, we have in order, we have index, and we have I, that is I minus 1, and that would be my left, and it will go till index. Okay, so it will go till index. Okay, no, what kind of messy code sometimes I write. I have index, have left, that will be left, then it would be go till I minus 1. This sleep waking me right, we'll solve it, be pre-order, in order, we have index, left would be I plus 1 and it will go till right, good, and then return the root, and now make the call here, and n is equal to pre-order dot size, and int index is equal to 0, return solve, that will take pre-order comma in order and 0 index till n minus 1. This shall be working right. Okay, we have index. Now there's a particular thing that could be confusing to some people, that I'm increasing the index only once, but I'm using pass by a reference one index. So when I will just increase in the index here, and all the times the value will be increased. So this can just get that value. It's not like that. It will also again access from 9. No, it will increase the value till index the find the value till where it will increase, and that will be fetched here. Sorry for the kind of thing, that kind of language. It's quite late. Pre-order index. What's the issue? What's this pre-order? Let's make this replace all of this. Might have made the issue. Try to run it. Still the same issue. Did I make mistake here? Okay, left comma I minus 1. What's the issue? Undeclared identifier I. Okay, so it's an undeclared identifier. Okay. This is inside a loop, so that's the thing. I need to int I is equal to left here. Let me just declare it here and just remove this. Just work this. Da, 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 da. Okay, so what's the issue now? 0 comma 0 int index. What's the issue now? Okay, so I can't pass 0 here. So let's pass index. That would be index. Okay, let's pass index. Let's see it works. If it works, it's fine. It's probably more than 9. Okay, so it works. Now for today, I think this much would be pretty much great. We'll move forward to new portion tomorrow.